Welcome to this deep dive into the future of forecasting. We're tackling a great question today. How can we combine probabilistic models with time series models to get the best of both worlds? This video is for data scientists, statisticians, and anyone keen on advanced forecasting techniques. By the end, you'll understand why this combination is crucial for robust predictions and how to implement it effectively. Modern forecasting research is rapidly evolving, moving beyond simple point predictions. The cutting edge lies in merging the strengths of different modeling paradigms to provide more comprehensive and actionable insights. So why combine these two powerful approaches? Each brings unique strengths to the table, and together they offer a more complete picture of future possibilities. Time series models like ARIMA, ETS, SARIMA, or LSTMs excel at capturing the temporal structure of data. They identify trends, seasonality, and autocorrelation, providing a solid foundation for understanding historical patterns. On the other hand, probabilistic models, such as Bayesian methods, Monte Carlo simulations, or probabilistic regression, are designed to capture uncertainty, distributions, and risk. They move beyond single predictions to provide a range of potential outcomes. By combining them, you gain significant advantages. You don't just forecast a single number. You forecast a distribution of possible outcomes. This means your forecast isn't just a point estimate, but a rich distribution of possibilities, reflecting the inherent variability and uncertainty in future events. This allows you to answer critical, probability-based questions. For example, what's the probability sales will exceed 100 units next month? Let's look at the general framework. If your time series is YT and features are XT, a time series model gives you a point forecast. But with a probabilistic extension, your forecast becomes a distribution of values, given all data up to the current time. There are several powerful methods to combine these approaches effectively. Let's explore some of the most popular and robust techniques. First, Bayesian time series models. Here, you place priors on time series parameters. For example, in Bayesian ARIMA, you define likelihoods and priors, and then use MCMC to sample the posterior distribution, giving you a full probabilistic forecast. Next, probabilistic deep learning. Models like DeepAR train neural networks to predict parameters of a distribution, like the mean and variance, instead of just a single number, providing a probabilistic output. Then there's simulation-based probabilistic forecasts. You fit a time series model, collect residuals, and then simulate future paths by resampling those errors many times using Monte Carlo methods. The distribution of these simulated paths becomes your probabilistic forecast. Optimization of errors also shifts. Instead of just minimizing mean squared error, you maximize the log likelihood of observed data under the predictive distribution. This approach is more aligned with the probabilistic nature of the forecasts. Now let's talk about practical tools you can use to implement these advanced forecasting techniques. In R, popular packages include BSTS for Bayesian Structural Time Series and Profit, which offers a Bayesian version for robust forecasting. For Python, you have a rich ecosystem with PyStan and PYMC for Bayesian modeling, Orbit from Uber for Bayesian time series, and Gluonce for probabilistic deep learning models like DeepAR. In summary, combining time series models for temporal structure with probabilistic models for uncertainty allows you to forecast a full distribution of outcomes. Methods like Bayesian ARIMA, probabilistic neural networks, and Monte Carlo simulations empower you to answer complex, probability-based questions and gain a deeper understanding of your data's future. Thank you for watching.